Ladies and gentlemen, please welcome our next speaker, Alberto Schiabel, presenting the topic, Supercharge your SQL with indexes, a practical introduction.
But I was a speaker here last year online, and this time I'm going to talk about SQL databases, and in particular about indices. Why should you care about indices? Well, they tend to make your queries fast. Today I want to give you an outline, a general. I want to give you an idea what you can do with them, what differences there are, and what are the most important things that you need to be aware of when dealing with them, because they can be quite tricky. We're going to use MySQL and InnoDB as an example, but most of the information we're going to share today are portable to other databases as well. And my hope is that even though you may be a very knowledgeable person on the topic, hopefully you will bring home some new information from this talk. And who am I? I'm Alberto Schiabel. I'm from Venice, Italy. I've been a software engineer, a consultant, a former startup co-founder. Currently, I'm mostly working with SQL, Rust, TypeScript, and WebAssembly. And most notably, I'm one of the maintainers of the Prisma open source project. It's basically an ORM, mostly for TypeScript developers. And one cool thing we do is we take an existing database, we pull all the information about it, like the database schema, and we port it into something that we call a Prisma schema that we use to generate type-safe queries, type-safe objects and methods for other languages. And we do so without you having to care about the specific SQL dialect of the underlying database. And one of the information we gather is the kind of indexes that the database has. But what is an index? Let's go through an analogy, maybe. All right, imagine you are a speaker here at DevDays. You traveled and you arrived here in Vilnius, and then you booked a hotel. What happens when you go to the hotel? Well, there is a guy or a person at the reception that's going to hand you the keys and going to tell you, hey, this is the room where you need to go to. But the hotel has several rooms and floors. So how do you find the right one? Do you go through every door? Imagine you have like 1,000 rooms. How much time are you going to spend looking for your own room? Probably you're going to be smarter about it and follow the signs. You're going to have some signs spread around the hotel that will allow you to quickly find your way to your own place. You're going to have basically going to tell you, hey, you have a set of rooms on this direction, a set of rooms on these other directions. Usually they are also kind of sorted to make sense of where you need to go. And in this analogy, the hotel is basically a database table, and the room is one column of database that you have an index for. Because these indexes are essentially directions. They allow you to quickly go to the data you need. So in practice, what are indexes? In the general sense, they are a data structure. Like, you might be familiar with primary keys already. They are a special kind of index because they are an index that contains the entire data. But most generally, an index is just an additional data structure that is separate from your data. It contains a portion, like some copy, and you'd use that to go back to your original raw data. There are several kinds. Like the major thing we can distinguish it is we have a primary key, which is like a unique identifier for every table, and then you have possibly many secondary indexes, which we can use to refine our own queries. We're going to see much more later. And why are they important? Well, simply for performance. They can make the difference between a 10-second query and a 2-millisecond query, for instance. If you run an application and serve many clients, your application is only going to be as fast as your slowest query, right? So you really want to tune your queries and try to make sense of and make use of everything that is available to you. And sometimes a linear scan, like a linear scan over all your entries in the table, that's just too much. If you have like millions or billions of rows, you don't want to wait for that. When should you create an index? You can't just create them every time you want. There are some constraints, there are some things to keep in balance. So the obvious answer is it depends. The idea is that you need to create as many indexes as you need, but only as few as you can get away with. Usually, there are some clues. When you look at your queries, there are some expressions like SQL blocks that probably will need an index. When you use order by, when you use where, when you use group by, for instance, the columns that you mention afterwards, in many cases, that might benefit from having an index. Of course, you need to measure that. And there are some tools at your disposal. Like you can just look at the indexes that exist for a certain table, or you can even ask the database to tell you what it plans to do with a certain query with the explain command. And usually, when you create your database schema, you start from the data at your disposal, or like from the data you expect to gather from an application. But for indexes, you can't just look at the data. It's not going to tell you much about how to speed things up. You need to look at your queries. You need to look at your data access entries, right? So if we go from data to schema, we need to go from queries to infer and to basically build our indexes up from the queries we expect to run. And what does MySQL documentation tell us about indexes? Like what happens if we don't have any index? Well, without an index, MySQL needs to begin from the first row of a table, then read through essentially the entire table, and then filter irrelevant rows in between. The larger the table, the more this costs, right? We want to avoid all of this. Let's look at an example. Here's a column of a user's table we are indexing. We have like 3 different values. On the left side, we see an ID that will be the primary key. We're gonna expand on that later. And imagine we want to run this query. We want to select all the users where the first name is Alberto, last name is Schiabel, and the users need to be active. What happens when you have an index? The database first goes through this index data structure. You see here we have a where first name equals Alberto. It's going to use that index. So it's going to pre-select essentially those 3 entries on the left side. And then from there, remember an index has a pointer to basically where the rows, the rest of the rows and the rest of the columns are written. So it's going to point to the table, and rather than scanning the entire table and filtering the things we need, it's going to just scan a portion of that table, just the portion that was indexed before. And that's kind of the beauty of it. From there, you can apply the actual filter logic, like you can refine, because the index usually only covers a small portion of your query, but that should be like just enough to get you by and make the query faster. But that's the gist essentially. And usually in InnoDB you have 2 main data structures. I'm just gonna cover one for today. There will be a B tree, like a balanced tree where you have more than 1 node per level. And the cool part is pretty much every database uses this data structure. It's been invented in the 70s, and everybody was like, okay, this is amazing. We're gonna use them for like the next 50 years, and they are still quite relevant today. They also use a similar version of them just for space queries. We're not going to bother with that today. Here's an example of a B plus tree. So you have like, you start with 1 root, and then you have like, you see each node can have multiple children. On the rows, we see ranges of IDs. Remember with the hotel analogy, where you have the signs, it tells you like room 401 to 410 are on the left, or 411 to 420 are on the right. That's the same thing. And we have a single root at the top. That's where every search starts. From there, we can have multiple intermediate levels. On a typical database, you might have like 3 or 4 intermediate levels. And then you have the leaf nodes at the bottom. And one thing is, that's where the keys for the index are stored in. And they are stored in alphabetical order, like a lexicographical order. This enables, for instance, for very fast ordered read of the index column. And in there, since you don't have like other nodes, the tree doesn't split any longer. You can just use binary search to find the exact column you need. And overall, the time is still going to be logarithmic rather than linear. So we avoid the full table scan. And notice how every leaf node is connected to the other. Right? This enables scanning from one to the next one. And leaf nodes are particularly important. Like in primary keys, they actually contain the whole data for your table. So not only you have the column, you have a pointer to every column for that specific record. Whereas in secondary indexes, which is essentially any index that is not the primary key, you're going to have just a pointer to the primary key. So at the end of the day, what matters is that every secondary index is going to have the primary key appended to it. And this, like from the space perspective, from the cost of adding an index to your database and to your table, you need to try to have the smallest possible primary keys, because they're gonna, the larger they are, the more expensive the queries and the storage is going to be. And what happens with a search? Let's try to do an example. We are looking for room 404. We start at the top. We go through, we look at the children we might have. Every children tells us what range of keys they have. We choose the appropriate one. If we're at the intermediate level, we continue. At some point, we reach the bottom, we reach the leaf node. And that's where we can just apply binary search to find the right column we were looking for. What operators and like what kind of operations can we benefit from in a query? Well, if you have an index column with a B tree in particular, you might use equality, you might use comparisons with like less than equal, bigger than equal, between, for dates, and then you might have some level of string matching. One important thing is that since these B trees, they start from a unique root, right? You can only query prefixes. So essentially, if you have a like expression, like give me all the columns that start with AB, and then they have a limited number of characters, and then they have a D character, you can do that as long as you basically benefit from the AB part of the string in the index, and the rest is going to be discarded. The database is going to need to work double for that. But you can't, for instance, look for something that ends with a special string. And also, inequality operators, generally, they do not benefit from an index. Like there's an example we can look at. So first of all, what kind of indexes do we have in our table? This is just a users table. We have a primary key, and then we have a bunch of unique indexes. We're not going to care right now. If we take a look at the query from before, like all the users where the first name is Alberto, last name is Schiabel, and the user is active, we're going to find one. But did we use an index? The explain commands tells us that no index was used. How can we tell? We need to look at the possible keys and the key column. Possible keys are the possible indexes that were considered by the database for this query, and the key was the actual index that was used. In this case, the key is null. No index was used. But if we look for something using the primary key, then yeah, we're going to see that the index was used. We see here, key is primary. Let's create a simple index, the simplest possible index. For instance, on the first name. All right, that will take a little bit. And now, if we try our query again, just explain, we see that this index was taken into consideration and it was also used. And about the operators we were looking at, let's try, for instance, to find all the users where the ID is between 1000 and 1100. Right? Those are a lot. It took just a few milliseconds, 9 milliseconds. What kind of strategy did the database use? It looked at the primary key. We see here. What if we want to, for instance, look at the birthday, at a special birthday? So we add an index on it. We select. Here we're using the between operator, which is supported by B plus trees. And if we look at the explain statement, it tells us, okay, right, the index was used, and the index was only like 3 bytes long, and we made use of it. It was very fast. If we drop the index, this might not be as fast. This took a few more milliseconds. If you have like more data, you will notice that much more. And what if we look for queries that start with a certain string? Can we benefit from an index? We do. We have an index on the first name, and we are using it. Here, key is IDX first name. We're using it. But what if, for instance, we're looking for something that ends with a certain string, and we don't know how it starts. As we see, no possible indexes were considered. This is not really possible out of the box. So that's something to keep in mind whenever you are indexing a string, for instance. Now we talked about primary keys. Most of you probably know already what a primary key is, but a few things to keep in mind. First of all, it's non-nullable. It needs to uniquely identify your an entry in your table. A primary key, again, is copied to every secondary index. So the smallest the primary key, the better, because otherwise your secondary keys are gonna be very, very large. And when you have several insertions, right? Usually in a normal app, you may have several reads, but at some point you can also have writes to your database. Every new insertion is gonna cause the tree to rebalance. The B tree needs to keep in balance, otherwise you have cases in which basically looking at one branch is going to take a linear scan, and we don't want that. Depending on the type of key you use, you might have those situations. So we're going to see how to avoid it. And also, you might run out of room. If you have a primary key whose where the number of bits is too small, basically, where you can only represent a small set of values, then at some point you might run out of room, and it will be difficult for you to migrate to a larger key space afterwards. Because when you think about that problem, it's always when you're like very deep in a maybe you're dealing with a production bug, right, with a production outage, and that's like the worst timing possible for thinking about how to expand your key space for the primary key. So maybe let's think about it beforehand. So like the simplest solution that I would recommend is using just begins, especially unsigned begins, with the auto increment keyword. They have the cool property that they are only 8 bytes long, but you can represent essentially 2 to the power of 64 values. That's a lot. Like those are billions of billions. They are very simple to explain. They are monotonic, so basically every new entry is gonna create is gonna bump the previous index by 1. They are very much performant, but also they might have some constraints or like some problems for you. If you expose your ID to any user, maybe in an API or in the URL of your application, then they might be predictable. That might be a problem in some cases. And the sequence essentially that generates those auto-incremented IDs is database dependent. If you migrate to another database, you might have problems synchronizing those. In most cases, you probably won't need that. You won't bump into that problem, but perhaps you will. And also, they are 2 to the power 64 bits might not be enough for you if you are, I don't know, a banking application, if you are working at Uber, Facebook. So there are other alternatives like UUIDs. Probably you already heard about them. They are typically just 128-bit strings. You can represent them as a 36-bit byte hexadecimal string. And then you have like this very nice example. You see some of the bits are reserved for like a version, a variant, but still you have like 122 bits available, and all of them are random. So you might have some collision, but you have a much larger key space. So that might be more beneficial for certain kind of apps. They can also be represented in binary, and that would be ideal because you can spare some space. Essentially, there will only be double the size of an unsigned begin, and I will recommend that. Most databases have like a data type specifically for this, but you can also use just binary 16. And an alternative to that would be the ULID, which is like the universally unique lexicographically sortable identifier. So one thing we mentioned before, whenever we insert a new row, we need to be careful about the rebalancing of the B plus tree. If we use sorted keys, like monotonic keys, such as the auto-incremented ID, or this kind of thing where you always have a timestamp at the beginning, then they're going to be naturally sorted. This will minimize the need for rebalancing. If you use a UID, where most of the bits are random, both at the beginning and the end, then you're going to have many more rebalances. It's going to be slower to index and to insert things. But ULIDs also have a bit more space. You use the full 128-bit, and they are very precise. Like you can't have any collision within 1 millisecond. They still have some problems though. And one problem is, well, before the problems, in textual form they are smaller than the ULIDs, so that's nice. They're only 26 bytes rather than 36. And if you represent them in binary form, they are the same size, 16 bytes. What's the catch? Sometimes they, you might have several microservices, and they might have a new insert request at the same time. And if that's happening at the same millisecond, and they have the same random seed, then you might have a collision there. And you might need to retry the insertion and then have some sort of like backoff mechanism whenever you're inserting things. Also, like begins, you mostly generate them from the database themselves, so you don't pass an ID from your application to the database. Whereas with ULIDs, most likely you're gonna generate the ID from your application code and then gonna insert it to the database rather than generating it directly from the database. Another cool part about ULIDs is that they are URL-friendly. Like they don't have some characters that you might confuse whenever you display them on a URL, like I and L. You only have one of them. There are also other alternatives where you just use a more compact alphabet, and like you have fewer strings available, smaller in size, like nano-ID. But you get the idea. I wanted to show you maybe some example about this. Like, I already have a bunch of IDs generated for this table. I don't know if I can make the results here larger, but just to make an example here, this will be the UID in text. This will be the ULID in text. And also like there are things in binary form. And we can take a look at how much they cost in size. So if we go through our table, we see that the key that costs the most in terms of size is the primary key. Remember, it holds not only the bit tree, but also the entire data. That's like 115 megabytes. We have like 500,000 records. And then if we see the ULID and the UUID, they weigh around 29 megabytes because they have the same size, almost the same size. The UUID in binary form, that will be around 60 megabytes. So, and if you have just the nano-ID with a smaller character set, you're gonna have like 50 megabytes. Remember, always try to have like the smallest size possible, and you can just track them and keep them in mind. Whenever you experiment with keys, or whenever you experiment with indexes, for that matter, try not to add them and drop them continuously. First of all, if you are in production, adding or reshuffling the keys may cause outages because you're essentially locking certain tables or large portions of your tables. What you want to do is either to apply them in the background, or maybe on a tier 2 database, or you might just toggle them. For any ID or for any index, you can turn them on or off. With this, alter table, alter index, the name of the index, and then you say, do you want it to be invisible or do you want it to be visible? And then if you take a look at the indexes again, you see here there's a column visible, and many of them are not visible, for instance, anymore. Right, back to the slides about secondary indexes. So again, those are any index that is not the primary index. And you might already be familiar with unique indexes and foreign key indexes, as well as unique constraints and foreign key constraints. While in MySQL, a foreign key constraint will automatically create an index for the key you're referencing to an external table, and for unique keys as well. Keep in mind, if you use Postgres, for instance, a foreign key constraint doesn't imply having an index under the hood. So if you run join queries with Postgres, you might not benefit from an index, but in MySQL, you always do. Again, what if you have a primary key, and then you also have a unique key, and they point, or like they index the same column? What do you think will happen? So ideally, you would imagine MySQL would be smart enough to figure out they reference the same table, they have the same, essentially the same data under the hood, so just don't create a new one. The primary key is also unique, so just don't create a new one. MySQL is not that smart. for good reasons, because it needs to be very fast at elaborating performance plans. So it's up to you to ensure that you don't have redundant indexes. And again, show indexes is your friend. All right, so we talked about creating and maybe toggling on and off indexes, but how does MySQL use the indexes we create for it? MySQL chooses the most selective index available. And to understand that, we need to introduce the concepts of cardinality and selectivity. So first of all, you have one big constraint. You might have any number of indexes in your table, but MySQL is only going to consider one per query. So you need to be very fast at selecting the best one for it, in most cases. And it's going to select the index that is expected to contain the fewest rows. So the least number of rows. Why is that? Because you want to filter as much as possible within the index before going back to the table, to like the filter version of the table, and apply further filters and groups and orders within there. So it kind of makes sense. And every index, if we take a look at, for instance, here, I think the show index was the one. But like every index keeps track of the cardinality. Here, you have a thing called cardinality. It's essentially the same as the count of unique values for that column within the table, but it's not exact. It's just some sort of statistic. And MySQL uses that to infer how many entries am I going to expect with that particular value. And based on that, it selects the most selected one. So the cardinality is just the number of distinct values in a column, and the selectivity is just the cardinality divided by the total number of rows in the table. And one question for you to see if this is clear is, what is the selectivity of a primary key? I hear 1. Does everybody agree? We can quickly check that. One moment. Here we go. All right, so this is, let's do this. I'm gonna get rid of this. This is it. This is the primary key, just the auto increment ID. This is the cardinality. This is the selectivity, and we see the value is 1. Which also brings us to a next topic. What if, rather than indexing the entire value, which might be a string, it might be a very long string, it might be a blob, it might be a text, it might be a varchar. What if indexing all of that was too painful, too costly for us? Could we get away with just a portion of the string? And in particular, could we get away with a portion of the prefix of the string? Well, we do. Prefix indexes exist for a reason, and indexing long strings is a really bad idea, because at some point the data structure is going to be so slow to deal with it that MySQL is going to give up and just avoid using the index in the first place and just go with a full table scan or choose another index. So let's take a look at what we can do. Imagine we have a column where we know that some values at the beginning, they are repeated, right? And if we find them, then most likely we are not left with many values to filter from. And one example would be the UUIDs or the ULIDs. And here is an example, for instance, with the ULIDs. These are the ones in textual form, and we're going to calculate the selectivity of essentially the prefix, starting from considering only the first 8 characters up to the first 11 characters. And we know that this ID, for instance, is unique, so it's going to have a selectivity of 1, and we want to find, rather than indexing the whole 26 characters, can we get away with a smaller number of characters to index? So if we query this, all right, we have it. Originally, we have the selectivity of 1. If we only consider 8 characters, we have 0.0012 as a selectivity. That is very bad. It means that if we index the first 8 characters, it's going to be useless, pointless. It's not even going to be used. If we index the first 9 characters, we have a selectivity of 0.037. That's better, but not quite enough. if we index one character more, 10 characters, we're going to have a selectivity of almost 0.9. That is very high, and that would be probably enough. And if we add even one more character, we're going to have a selectivity of 0.9969. So what can we get away, what do we infer from this? Rather than having an index covering the whole string that is 26 bytes, we can just get away with the first 10 bytes. How do we do that? We alter the table, we add an index, and when we mention the index, the column name, we open a parenthesis, we specify just the number of bytes that we want to consider, or actually the number of characters. And if we do that, and we also evaluate how much these indexes are costing on disk, we can see that the index we just created is only like 13 megabytes, whereas the index on the ULID column, like the whole thing, is more than double. It's 28 megabytes. So we see we can benefit from these kind of things. And this especially applies to whenever you're looking for values columns that are hashes, UIDs, ULIDs, or maybe if you have like a search with a type ahead in your application, and your queries usually start with users write something and they expect an auto completion afterwards, and you don't need like crazy text inference APIs, then you might get away with just a prefix index. It's gonna make your queries much faster. What about postfix? What if remember, MySQL is not really made for that, but there are a few adjustments you can make. You can still rely on prefix indexes if you maybe generate a column that is just the original column in reverse form, right? So the prefix of the reverse column is just the postfix of the original column. Or you might use a more advanced structure called the full text search index. I recommend you to take a look at that. We're not going to go through it right now. But also you might try to, in a specific domain, like if you have an email of a user and you want to query the domain of like the number of unique domains you have for the users in your system, you might just extract anything that comes after the @ sign of that string. You paste that in a generated column, and then you just apply an index to it, and that can be quite fast. For instance, if you have this kind of questions in your database. So far, we've only seen a single index, or like a single index using a single column. Can we do more? Can we use maybe multiple columns at once? And if so, what happens? How does MySQL react? Yes, we can. There are some things to be aware of. The idea is that you can have up to 16 columns per index, and whenever you declare them, essentially just have you declare the index name and then all the columns, and it's just a list. That list is considered as a sequential array. So essentially the position of the column within the index matters, and it matters a lot. In queries, MySQL is only able to use the indexes if the columns are basically accessed in the same order in which they are declared in a multiple column index. And the idea is that you just go left to right. It doesn't necessarily mean that you need to declare them left to right in the queries themselves. It just means that if you have certain filters, and for instance you need the column number 1 and the column number 2, you can't just omit column number 1 and expect the index to kick in. This is much easier to be observed in an example. We have this query here. We're looking at the users where the birthday is essentially in December 1997. The last name starts with SCH, and the users need to be active. We have a bunch of them. If we run the explain query, we see we have no possible keys, no possible indexes for this kind of query. What happens if we create a new multi-index using the first name, the last name, and the birthday? We create one. It takes a little bit. If we rerun the query, and like the explain query, again, nothing really happens. Why is that? Because we are not using the first name here. Like if we use the first name, and perhaps we select my name, Now we have one possible index to be used. Actually, we have more because we have one index on the first name alone and one index on the first name, last name, and birthday. But MySQL chooses this first name, last name, and birthday. Why? Because it has a higher selectivity. If I get rid of birthday here, this is still gonna work fine with that index. Why is that? Because basically we're filtering by first name and then by last name. We didn't use the birthday part of the index, but that doesn't really matter. And from a visual level, it's kind of like this. The index now has more than one column, in this case just two. We still want to retrieve just a same query as before, right? By the way, notice how we are ordering by first name, and then if possible we're also ordering by last name, but the first name order is more important. We apply the filter beforehand, so essentially the only actual work we're going to do on the table is going to involve IDs 21 and 23. From there we're going to fetch the other columns that we need, for instance the is active, so we're just going to apply a search in 2 rows rather than 5 in this example. And notice that it always begins with the first column we declared. First we filter there, then we filter on the second column, and so on. And once we have the whole set in there, we apply the rest of the conditional logic that SQL requires. Yeah. And finally, you may wonder, all right, so can we apply, I don't know, partial index or multiple column index to unstructured data, such as JSON? Many of you probably know that Postgres supports JSON, but I was surprised to know that MySQL also supports it. It does, but you can't really do much by default. So what happens, for instance, if you have a table like follows? You have an ID and you have a data. The data column is just a JSON. It's not nullable, but it's JSON. You don't really know what kind of keys to expect in there. What if you want to add an index in it? We're gonna have an error, and actually let's see that firsthand. I don't want you to just trust me on that. I have an error here. It says that the JSON column data supports indexing only via generated columns on a specified JSON path. This also implies that if we try to run a prefix index, like on the initial part of the JSON blob, that's just not going to work. It's going to be useless. What does it mean to have a specified JSON path? Essentially, you need to select one key from that JSON. So first of all, you want to take a look at it, perhaps, just the first few entries. You realize it has a certain structure here, and some keys are repeated. And maybe you want to, maybe they are repeated, like the same value appears more than once. And you may want to perform queries on it, or maybe aggregations on it. For instance, we have some types. These are sensor data. We have some weather information. We have some temperature information, pressure information, and we might also have IDs, like the unique IDs from the machines that are sending us this data. We know that the maximum size they have is 36, so perhaps we can just create a new generated column that matches that UID data from, maybe the syntax is a bit tricky to explain. This just says, start from the column that is a JSON and extract the first key, basically $.uid, there will be $.column, right? And if you do that, and you start querying the data, now you see you have an additional column here, this additional UUID. And can you apply anything to it? Well, if you run something, we don't have any ID on it. We don't have any index on it. But can we do more? Well, we could create, for instance, an index, a prefix index on it. Remember, this column didn't exist before. And now, if we perform this query where we're filtering by a specific UUID that didn't exist in the original data, now we see that we are considering using the index and we're actually making use of it. And this can make, especially when you have a large amount of JSON, this can make things so much faster. What do I want you to remember from today? We looked at several different things about indexes. First of all, indexes matter for performance. But don't get too eager to use them. You need to look at your queries first, and only afterwards you can kind of understand what kind of indexes you might need. And always try to benchmark. Try to benchmark, possibly not in production, but with a large set of data entries, and see, is this query even really making use of the indexes I planned for it? Is this query, does this query even need an index? Perhaps it's just a report where you don't, besides grouping, you don't need to do much. And another thing is, adding indexes has a cost, but also the not having indexes might be more expensive. If you use certain database as a service, such as PlanetScale, you pay based on the number of rows that the database reads, right? You also have egress fees, right? But the major cost is how many records is this database going to look at before providing the result set that I'm going to use for my own application. And if you don't have any index, and if you don't have like proper structure for your data, then you're gonna probably have like millions and millions of record rows, record scans every time you have a simple query. And those really accumulate very fast. You might gonna end up paying more than you allotted for the budget of your project. How do you avoid that? You try to add indexes where it matters, and you need to analyze them. Another thing is, every secondary index, just remember, they have a copy of the primary key. So try to make the primary keys as small as possible, but also not too small, otherwise you're going to run out of room and you're going to have a painful time with migrations. And secondly, if you use multi-column index, make sure that you access them in queries in a way that makes sense. If you have like 3 columns and you only access the last 2 columns, then you're not going to make use of the index you created. Just through, again, think about prefixes. You need to use the first n columns of your multi-column index, and then it's gonna kick in, and the database will make you much happier. And also, sometimes you just need generated columns. You don't need to store them on disk necessarily, but you might work with unstructured data, such as JSON, and you might need to perform certain filters on it. And the only way you have currently to have indexes on it is to generate things, such as we've seen with JSON columns. And that's all for me. If you want to learn more about indexes, here there are a few resources. I'm going to share the slides. I'm not sure how, but I have a link online that I can share with you all. Thanks so much for having me here.
Thank you for your presentation and this very valuable information on indexes and how to make the use of your database. Do we have questions in the hall here right now? Okay, you can think about it, and let's jump on to a couple of slider questions until we have time. So first one, generated column plus normal index versus function-based index. What's your take on it?
Function-based indexes, first of all, I always forget their syntax, but in most cases they are equivalent, like you use them for the same things. For instance, for the JSON example, you could use these function indexes. If you use an ORM or like other type of abstractions of your database, most of them have no idea how to deal with function indexes, so you might have a bit of a problem there. In general, I would say don't overcomplicate it. Like I still have to encounter a situation where I really needed them. But if you do, please come and talk with me afterwards. I'll be curious.
Thank you. Next one would be, how do you go about analyzing trade-offs for deciding the amount and size of indices? Any more rules of thumb other than list indices as necessary?
It really depends on how much do you know about your queries beforehand. So if you can plan ahead, just take a look at your queries, take a look at what kind of columns they access for a specific table. And if you have joins, always remember to index the joins. And if you have maybe a multi-column, I don't know, you have a many-to-many relation, right? You might benefit from having perhaps a primary key that is a multi-column, where you have basically one column for every relation you're joining in there. That's going to make things faster. Besides that, this is like one case I didn't mention in the slides, but beside that, there are no more rule of thumbs. Like it's just it. You need to look at analyze, you need to look at your query plans, and that's about it.
Okay, then 2 blitz questions. One is, what would happen if you index every column?
It will work, but if you just use single indexes, it's not going to be that useful, because the moment you filter by one, remember that MySQL always chooses a single index per query, so you're just going to have a lot of wasted disk space. Yeah, don't do that.
Okay, it's a waste. What is a perfect, most wanted selectivity?
The highest you can get. Like if you have a unique key, that's the best one. Whenever you have a key that filters by a single ID, like that's the best selectivity you can get.
Alrighty, then we have still time for one more question, which is, what tools could you recommend to audit the queries which could be considered for indexing?
Oh, so I didn't plan ahead for this, but there is one tool we just released, I think last week, from Prisma, called Prisma Optimize. It's going to take a look at all the queries you run via Prisma, and it's going to basically order them by runtime inefficiency. And from there, we give you insights like, this might benefit from an index in this query, in this column, or this other column. Or you might use this other kind of query to have the same result. I don't have a link right now because this was not a sponsor talk, but if you are curious, contact me afterwards.
Alrighty. Questions in the hall? Still? None? Alrighty, then again, thank you for your talk.
Thank you so much.
And you can catch Alberto outside and ask him more questions. Thank you.